Hello and welcome to Acala's ETHDenver workshop. Today we'll be creating an advanced escrow smart contract. In this tutorial, we'll dive into Acala EVM Plus smart contract development using Hardhat development framework. We'll start with a setup, build a smart contract, and write deployment and user journey scripts. The smart contract will allow users to initiate escrows in one currency and for beneficiaries to specify if they desire to be paid in another currency. Another feature we'll familiarize ourselves with is the on-chain automation using a pre-deployed smart contract called Schedule. Using it will allow us to set the automatic completion of the escrow after a certain number of blocks. So let's jump right in. First, we need to set up. So you need to create a folder in which the project will live. For me, this is the Advanced Escrow folder. In it, we have to initiate a Yarn project and add Hardhat as a development dependency. So when you initiate the Yarn project, you can just press enter for each option because this is a example tutorial, so we don't need to set up anything. Adding Hardhat as a development dependency will allow us to initiate a Hardhat project. To do that, we'll need to use yarn Hardhat command. So Hardhat will ask us what kind of project we want to set up. And for this tutorial, it's enough to create a basic sample project. So we just select enter and we accept all of the changes that it's offering. Once all of the dependencies are installed, we can start configuring the Hardhat config. Here we'll add two networks. One will be local development network, which we will call Mandala, and the other one will be public test network, which we will call Mandala PubDev. Both of the networks have to reside within the network section of the module exports. Mandala, a local development network, will be reachable at localhost. We'll be using port 8545. This is the default port for most of the EVM instances. We have to create account section as well. Here we'll define the mnemonic and the derivation path to use in order to get the desired accounts. For the local development networks, we'll use the mnemonic of the pre-funded local development accounts. The mnemonic words are Fox, Site, Canyon, Orphan, Hotel, Grow, Hedgehog, Build, Bless, August, Weather, and Swarm. The derivation path for this mnemonic that we want to use will be 40, 60, 0, 0. And the chain ID of the local development network is 595. To speed up the definition of the public test network, we can reuse most of the mandala configuration. We just have to rename it. We have to change the URL. URL in this case will be HTTPS, so we'll be using secure protocol to communicate on the internet. And then TC7 ETH.aca/dev.network. In the account section, you should not use the mnemonic we just described. You should have your own mnemonic. The derivation path can be the same, but you can also change it if you wish. For the public test network, we should also set a timeout. So we should increase the default timeout just in case there is a bit more traffic on the network. So we'll increase it to 60,000 milliseconds or 60 seconds, which means that we'll accept 1 minute of wait times. Now we can save the hardhat config. And with that, our project is ready for development. Now we need to add the smart contract. So the advanced escrow smart contract, which we will add is in the following section, will still leave some areas that could be improved. Advanced in the name is referring to the use of the pre-deployed smart contracts in the Acala EVM Plus rather than its function. So when two parties enter into an escrow agreement using the advanced escrow smart contract, the party paying for the service first transfers the token from one of the pre-deployed ERC20 contracts into the escrow smart contract. The party then initiates the escrow within the smart contract, so we'll refer to that party in the initiator. Initiator of the escrow requires both the contract address of the token being escrowed and the wallet address of the beneficiary of escrow. Upon initiation of the escrow, the smart contract exchanges the tokens coming into escrow for aUSD. Then it sets the deadline after which aUSD is released to the beneficiary, and the beneficiary also has the ability to specify which tokens they want to receive from escrow. The smart contract exchanges the aUSD it's holding in escrow for the desired tokens upon completion of escrow. This means that you can initiate the escrow with ACA, and the smart contracts will exchange the ACA for aUSD to hold it until the completion of the escrow, and then the beneficiary can decide that they want to be paid out in DOT, which means that the smart contract will swap aUSD for DOT before sending it to the beneficiary. We'll also allow for the escrow to be completed before the deadline, with the ability for the initiating party to release the funds to the beneficiary manually. Hardhat has already created a smart contract within our contracts folder. So this smart contract is called Greeter, but we will create an advanced escrow smart contract. So what we can do is rename the greeter delete the content of the smart contract, rename it, and delete the import statement. And now we can start with the imports. So we'll use two dependencies to import into our smart contract. One will be Acala Networks contracts dependency, and the other one will be OpenZeppelin contracts. To add them, we first had to add them as development dependencies. We want to use the version 4.02 of Acala network contracts, so we need to specify that when we're adding the dependency. And for the OpenZeppelin, we want to use the version 4.4.2, so we need to specify that as well. So we will be using the IDEX and iScheduler precompiled smart contracts from Acala network contracts, and ERC20 contract from OpenZeppelin contracts. So as you can see, we now have Acala network contracts as well as OpenZeppelin contracts as our development dependencies. Let's import the smart contracts that we need. With that, we've imported the IDEX smart contract. Let's now import the ERC20 smart contract from OpenZeppelin. And we've imported ERC20 smart contract. The last import that we need to do is for the scheduler. As the pre-deployed smart contracts always have the same address, no matter the network, we also need to import the address utility that is included within the Acala network contracts dependency. So let's do that as well. Now that we have sorted out all of the imports, we need to make sure that our AdvancedEscrow smart contract inherits the address smart contract utility in order to be able to access the addresses of the pre-deployed contracts stored within it. We have to add inheritance to our AdvancedEscrow. Now we'll be able to use address to get all of the information. So if we take a look at the dependency, you can see that we can just call the name of the pre-deploy and get its address. Let's use that. We can finally start working on the actual smart contract. We'll be interacting with the pre-deployed DAX and scheduler smart contract, so we can define them at the beginning of the smart contract. Here we're using the address utility. And we want to define scheduler as well. Our smart contract will support one active escrow at a time, but we will allow its reuse, which means that once the escrow is completed, another one can be initiated, but two cannot be live at the same time. Let's add a counter to be able to check the previous escrows as well as the escrow structure. So let's first add the counter. It will let us know how many escrows there have already been. Okay, so within the escrow structure, we'll define the address of the initiator, which will be the address of the party that initiates the escrow. There will also be the address of the beneficiary. This is the party that receives the funds after they've been released from escrow. We also need to store the addresses of the ingress and egress tokens. Additionally, we need to store the aUSD value of the escrow. And we also need to store the deadline. So the deadline will determines in which block should the scheduler smart contract automatically release the funds from the escrow to the beneficiary. One last thing that we need to do is set a Boolean value of completed, which is used to check whether the latest escrow is still active or has it been completed yet. This check will also allow us to make sure that the same escrow is not paid out twice. We also need a mapping that allows us to query the escrows based on their IDs. We want to make the mapping public as to generate a getter once we compile the smart contract. The constructor in itself will only be used to set the value of number of escrows to 0. So while the Solidity is a null-state language, it's still better to be explicit where we can be. So now we can add the escrow update event. This event will have 4 different values. One will be address of the initiator of the escrow. The second one will be the address of the beneficiary. The next one will be unsigned integer value, depicting the aUSD value of the escrow. And the last parameter will be a Boolean value called fulfilled. This Boolean will let the listeners know whether or not the escrow has been completed. Let's start writing the logic of the escrow. As we said, there should only be one escrow active at any given time, and the initiator should only transfer the tokens to the smart contract before initiating the escrow. When initiating the escrow, the initiator should pass the address of the token they allocated to the smart contract as the function call parameter in order for the smart contract to be able to swap that token for aUSD. All of the escrows are held in aUSD, but they can be paid out in an alternative currency. None of the addresses passed to the function should be 0x0, so 0 addresses, and the period in which the escrow should automatically be completed, expressed in the number of blocks, should not be 0 as well. So all of this happens within the initiate escrow function. Let's build it. We have address of the beneficiary. We have address of the ingress token. We have unsigned integer of the ingress value. And we have unsigned integer of period in which the escrow should be completed. While the deadline is depicted in a target block number, the period should represent the number of blocks in which the escrow should be completed. The visibility of this function is public, and it returns a Boolean value depicting successful execution of the smart contract. So let's add our checks. The first check will make sure that the previous escrow has been completed. But we'll also need to make sure that we can initiate the first escrow. So we have to check whether or not the number of escrows is 0, or if the latest escrow has been completed. We also have to let the caller know if this check has failed. Next, we need to make sure that the beneficiary address is not a 0 address. And we also need to notify the caller if that is the case. The next check we'll be adding is that the period is not 0. And we have to notify the caller if it is. Now we have to instantiate the ingress token smart contract in order to be able to verify that the smart contract's balance is greater than the ingress value. For this, we'll use a local variable called contract balance. And we'll instantiate the token ERC20 smart contract using the ERC20 OpenZeppelin import. We'll call the balance of function of it and pass the address of this smart contract. Now let's add the check. So we want to make sure that the contract balance is greater or equal to the ingress value. If it's not, we want to make sure that the caller knows that. Our checks are now complete. The next thing that we need to do is instantiate the aUSD token smart contract. We'll once again use the ERC20 import. And the address utility. We have to make sure that we're only allocating the swapped amount of aUSD to the escrow, which means that we have to make sure that if the smart contract already had an aUSD balance, we're not allocating all of its balance to this escrow. To do that, we need to make sure that we check for the initial aUSD balance before we make the swap. So the next thing that we need to do is set the path of the swap. To do that, we first need to instantiate the array of addresses in the path variable. There will be two addresses within it. In the first place, In the first place of it, on the index of 0, we'll allocate the ingress token address. On the second place, with the index of 1, we'll set the address of the aUSD instance. Now we'll call the pre-deployed DEX with the function called swap with exact supply, because this is our ingress value. And since the swap with exact supply returns a Boolean value which signals a successful execution of the function, we can put that within the require statement so that if the swap fails, our execution will stop as well. We already defined path. Our supply amount is our ingress value, and our minimum target amount is 1, as we're accepting any kind of value there is. Now we need to make sure that we fetch the final aUSD balance of the smart contract. Now that we have our final aUSD balance, we can schedule the completion call with the schedule smart contract. Since there are a lot of parameters, we'll break this line down into multiple lines and format this nicely first. So the contract address that we want to call is this one. The value that we want to send with the call is 0, but we want to set the gas limit to 1 million, just to be sure that the execution is successful. Our storage limit will be 5,000, and our minimum delay is the period in which the schedule should release the escrow. And our input data will use the ABIs encode with signature and we'll pass the into it. We won't be passing any additional arguments. Complete with escrow will be the function to complete the escrow. The last thing that we need to do is store the values that we've just gotten from the function into escrow structure. To do that, we can initiate a current escrow. This way, we'll only call current escrow instead of this one. Now, let's set its values. The initiator of the current escrow is the sender of the transaction. The beneficiary of the current escrow is the beneficiary that was passed to the function call. The ingress token is the ingress token that was passed as well. The aUSD value of the escrow is equal to the difference between final aUSD balance and initial aUSD balance. The deadline of the current escrow is the current block number plus the period that was passed as an argument to the function call. The last thing to do is to increase the number of escrows. Here we go. I just have to fix the typo. Now that the escrow is stored in storage, we just have to emit the escrow update event. So the initiator was message sender, the beneficiary was the beneficiary. The aUSD value of the escrow is stored within the current escrow, and it hasn't been completed yet. All we have to do is return true boolean, which signals successful execution of the function. As you might have noticed, we didn't set the egress token value of the escrow. This is up to beneficiary, and the default payout is aUSD, but the beneficiary should be able to set a different token if they wish. As this is completely their prerogative, they are the only party that can change this value. To be able to do so, we need to add an additional set egress token function. Only the latest escrow egress token value can be modified, and only if the latest escrow is still active. So let's create the function called set egress token, which will accept one argument, which will be of type address, and we'll call it egress token underscore. Its visibility will be public, and it will signal successful execution by returning a Boolean value. So the first check that we need to add is that the current escrow is not completed yet. And we need to make sure to notify the caller of the function if it is. The next check we'll be adding is that the sender is the beneficiary of the escrow, since they're the only ones able to set the address token address. And we need to notify the caller if that's not the case. Now we can update the address of the address token. And with that, our function is complete. And the last thing we did was signal the successful execution of it. Another thing that you might have noticed is that we scheduled a call of complete escrow in the schedule call. But we don't have this function defined yet, so we need to add it. The function should only be able to be run if the current escrow is still active and only by the AdvancedEscrow smart contract or by the initiator of the escrow. The smart contract is able to call the complete escrow function because it passed a pre-signed transaction for this call to the scheduler smart contract. The function should swap the aUSD held in escrow for the desired address token if one is specified. Otherwise, the aUSD is released to the beneficiary. Once the funds are allocated to the beneficiary, the escrow should be marked as completed. An escrow update event notifying the listeners of the completion should be emitted. So let's add the complete escrow function. This one will take no parameters. Its visibility will be public, and it will return Boolean value to signal successful execution of the function. So first thing that we'll do in this function is to instantiate the current escrow. Now we'll add some checks. So the first check that we will add is to check whether or not the escrow has already been completed. And we have to notify the caller if it has been. The next check that we'll add is whether the caller is the initiator of the escrow or if it's the smart contract. And if the check fails, we need to notify the caller of its failure. Now we have to make sure that we swap the aUSD for the address token if one is specified. F1 is specified, we need to instantiate it using the ERC20 import. We need to make sure that if we have the initial balance of this token, that we're not transferring all of the balance, so that we're transferring only the change in balance or only the tokens that we'll get from swapping the aUSD. Once again, we have to specify the path of the swap. Now, the first element in the path array is the aUSD. And the second element within path will be the address token. We'll use the same function as we did before. So we'll call DEX's swap with exact supply, and we'll pass path to it, and our supply amount will be current escrow's aUSD value, and the minimum target amount that we're willing to accept is 1. If the swap failed, we have to notify the caller. Now we need to get the final balance of this smart contract. And once we have the final balance of the smart contract, we can transfer the tokens that we got from swapping with the pre-deployed DAX to the beneficiary. And the amount that we'll be transferring is the difference between final balance and the initial balance. But there is another case. So if the beneficiary decided that he's okay with being paid in aUSD, then we just need to transfer the aUSD value of the escrow from the AdvancedEscrow smart contract into their account. We do that by instantiating the aUSD token smart contract. and transferring the tokens. And the amount in this case will be just the value of the current escrow's aUSD value. Once we've released the funds from the escrow, we have to set the current escrow completed boolean to true. This allows the smart contract to initiate additional escrows. Last thing that we need to do is submit the escrow update event. To it, we'll pass the current escrow's initiator, current escrow's beneficiary, its aUSD value, and true to signal that the escrow has been completed. And by signaling successful execution of complete escrow, our smart contract is ready. In order to be able to compile our smart contract with the yarn build command, we need to add the custom build command to package.json. We do this by adding a script section below the dev dependency section. And within it, we'll add a build option, which will use hardhat and its command compile. Now we can use yarn build in order to compile our smart contract. So the issue here is that hardhat config mnemonic for Mandala pub dev is not really a mnemonic. So I'll just enclose it. And that passed. So yarn build command created artifacts directory, and within it the compiled contracts that we use. So DEX, scheduler, and utils, as well as token and advanced escrow. Now we're ready to add a deploy script. So initiating hardhat also created a scripts directory, and within it a sample script. We'll remove it and add our own deploy script instead. So I just created a deploy.js script, and we'll use this one to deploy our advanced escrow smart contract. So first, let's create the skeleton of the script. Let's add the main function definition, and then make sure that when the script is called, it's executed. When deploying to the Acala EVM Plus, we have to pass the transaction parameters to the deployed transaction. This is a result of the storage rent that has to be paid in addition to the transaction costs. To get the correct values to pass to the transaction, we can import the Acala network ETH provider's dependency. But first, we need to add it. Once added, we'll import it at the top of the deploy.js script. We'll import the calc Ethereum transaction params from Acala network ETH providers. In addition to that, we'll also set two constants. So one is TX fee per gas, which we'll set to 1999999 46752. And the other one is storage by deposit, which should be 1 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0. At the beginning of the main function definition, we'll set the remaining transaction parameters. We'll also need to get the current block number, as we have to specify the block after which the transaction is invalid. If we hard-coded this parameters, then the script would eventually fail on the public network. Now we can create the ETH params. We'll be using the calc Ethereum transaction params that we imported. But we'll be setting additional values. We'll set the gas limit to 21,000,010. We'll set the valid until parameter dynamically using the block number, adding 100, and casting that to string. Our storage limit will be 64,000,010. And we also need to include TX fee per gas, as well as storage byte deposit. Now that we have the deployed transaction parameters set, we can deploy the smart contract. We need to get the signer, which will be used to deploy the smart contract. Then we instantiate the smart contract within the contract factory and deploy it. passing the transaction parameters to the deployed transaction. Once the smart contract is successfully deployed, we'll log its address to the console. Let's retrieve the deployer. Let's get the contract factory of the advanced escrow. And let's deploy it while instantiating it. We still have to pass the gas price which is calculated from the ETH params that we passed, as well as the gas limit, which is also calculated from the ETH params we defined above. The last thing that we need to do is to log the address of the advanced escrow to the console. And with that, our deploy script is ready to be run. In order to be able to run the deploy script, we need to add a script to the package.json. To add our custom script to it, we'll need to place it within the scripts section. We'll add two different scripts. One will be utilizing the local development network, and the other one will be utilizing Mandala public test network. So deploy Mandala will be our command, and to it will use hardhat, and it will run scripts deploy.js on the network. And we can copy this line because the public development network will use the pubdev as an identifier in the command, and the only difference here will be that it will be using Mandala pubdev network. And with that, we're able to run the deploy script using yarn deploy Mandala or yarn deploy Mandala pubdev. Using the latter should deploy the smart contract successfully if you add your own mnemonic. So I'll be using the first one on the local development network that I'm running in the background. I might have made a mistake. Oh yeah, here it is. Passing the mnemonic. Let me revalidate that. So it was Fox site Canyon, Orphan, Hotel, Grow, Hedgehog, Build, Bless, August, Weather, and Swarm. It was the last letter in the mnemonic. I want to validate that the path is correct. Oh, I misspelled the path as well. It was 446000. And as you can see, there was some output that was generated by the dependencies of our dependencies. But the last line shows us the successful deployment on the local development network.